Okay, let's say you were given a vector field. This one's just going to be in 2 dimensions. Okay, and this is your vector field. X in the I direction plus Y in J direction. So at every point X and Y, you're given a vector back, and that's what's called a vector field. Now what we're going to do in all these problems is we're going to calculate the divergence of the vector field, and we're going to calculate the curl of the vector field. Okay, so never forget, I want you to always burn this in, the del operator is always equal to the partial with respect to X in the I direction, or the X direction, plus the partial with respect to Y in the J, plus the partial with respect to Z in the K. That's what the del is actually equal to. So now we're going to use that to actually go ahead and calculate the, let's go ahead and calculate first the divergence of the vector field F. Okay? So what we're going to do is we're going to actually dot these 2 things together. Okay? So when you dot 2 things together, you know you dot component by component, so what you'll have is the partial with respect to X of X, because we're just taking this and kind of multiplying it together. So the partial with respect to X of X plus the partial with respect to Y of Y. Now there's a partial with respect to Z, but there's no Z component, so it really just drops away. Okay? So the divergence of this vector field is equal to what? The partial with respect to X of X is 1. Partial with respect to Y of Y is 1. Okay? So the divergence of this thing is just equal to 2. Now notice the divergence is a positive number, so it's a sourcing type of field. And notice that the answer is not dependent on X and Y at all, which is actually pretty unique. Most of the time when you calculate the divergence, depending on where you are, the divergence will be a different value. But for this particular magnetic vector field, no matter where you are in the XY plane, the divergence is always equal to 2. Okay? Let's go ahead and calculate the curl. Let's go ahead and calculate the curl. So what we're going to do for the curl, we're going to calculate the curl of this field. So we're going to take the determinant of a matrix. Okay? You're going to have the I, you're going to have the J, and you're going to have the K. Okay? We're going to do del first, so you get partial with respect to X, partial with respect to Y, partial with respect to Z. And then we're curling into F, so I put the ith component, which is X, the jth component, which is Y, and the kth component, which is 0. There is no k component, so I'm just going to put a 0 here. I'm doing it this way mainly just to be complete, okay? I mean, you don't have to do it this way, but this is the way I really like to do it. So first, let's work on the I component. Working on the I component, I cross this out and I cross this out, okay? So I'm going to work on these guys right here. So inside I'm going to have the partial with respect to y of 0, partial with respect to y of 0, minus the partial with respect to z of y going this direction. So you're taking the determinant of this minus this, okay? We'll evaluate it all later. Let's go ahead and continue on. Minus j, anytime you work on the j component, you have to put a negative sign. We're going to cross this out, we're going to cross this out, so you have the partial of x with respect to x of 0, minus, because you're doing this one and this one, minus these two, partial with respect to z of x. Okay? And then the k component, which is going to be this component here, you're going to have this, partial with respect to x of y, this guy, minus partial of y of x. Make sure you understand where this comes from. Working on the y first, you cross out this. You're going to take the determinant of this little quadrant. Partial of y of 0 minus partial of z of y. Working on the middle one, you have a minus j. You always have to put the minus like this. Partial of x of 0 minus partial of z of x. And then working on k, you cross these out mentally. Partial of x with y, partial of y with x. Now, I think you'll find an interesting result, what happens here. In the I direction, what do you have? Well, the partial of 0 is 0. The partial derivative of y with respect to z is 0. Okay? You should remember that from your partial derivatives. So you have 0. Minus j. Partial of with respect to x of 0 is 0. partial derivative of x with respect to z is 0 because it's a constant with respect to that. That's just, remember back from the partial derivatives, plus k, partial derivative with respect to x of y is 0, and then partial derivative with respect to y of x is 0. So basically what you get here is a big fat 0. There is no curling going on. Basically you calculate the curling and every component gives you 0. So for this particular vector field, there's no curling going on. If you were to plot that vector field, you would not see any rotational type of curling going on for that vector field, okay? So we calculated the divergence was positive everywhere and the curl was 0 everywhere. And that's sort of a little bit of a special case, but that's exactly what we found, okay?